In this video, we're going to talk about the kinetic theory of gases. The idea that all familiar matter is made up of atoms goes back to the ancient Greeks. Democritus proposed that if one was to cut a piece of iron into smaller and smaller portions, there would be a portion which could not be divided further. This smallest piece he called an atom, which means invisible. Another of the scientists working with gases, John Dalton, reprised the theory of atoms. His experiments led him to propose the foundational postulates of modern chemistry. The first of these was that the elements, which he called fundamental materials, are made up of atoms, and that all atoms of a given element have the same physical properties, such as mass and size. From Dalton's principles, it followed that properties of materials are determined by the properties of the atoms in the material, the motion of those atoms, or molecules, and their interactions. In fact, the properties of matter we have studied so far, the thermal expansion, melting, boiling, cooling points, and heating, can be explained based on the concept that matter is made up of atoms. The kinetic theory of gases is the first of the theories of materials. It relates the motion of the atoms, or molecules, which comprise a gas, to the thermodynamic properties of the gas. The kinetic theory of gases provides us with a better understanding of the following: 1. The temperature, 2. Heat, 3. The internal energy, and 4. The pressure of the gas. The study of a real gas can be mathematically complicated. We would have to consider the following things: 1. The motion of the molecules in the gas. 2. The motion of the atoms inside each molecule. 3. Whether the molecules repel or attract and even stick together. And 4. Whether they will combine to form different molecules. In our application of the kinetic theory of gases, we will be using a set of simplifying assumptions, which we call the ideal gas model. So here are the assumptions of the ideal gas model. 1. The gas consists of a very large number of particles, whether they be atoms or molecules, inside a container. 2. The walls of the container are rigid and very massive. 3. The particles behave as point particles. Their size is small in comparison to the average distance between particles and to the size of the container itself. 4. The particles are in motion. They obey Newton's laws of motion. Each particle collides occasionally with a wall or the container. These collisions, when they occur, are perfectly elastic. Which of the following is not included into the assumptions of the ideal gas model? A. The number of molecules in a container is very large. B. The molecules interact when they collide with each other. C. The molecules interact all the time during their motion because of intermolecular forces. D. The collisions between molecules are perfectly elastic. E. The size of the molecules can be ignored. Okay, so let's see if you chosen the correct answer. The correct answer is C. The part C is not included in the assumptions. So now let's talk about pressure. The first physical quantity we will model is with kinetic theory is pressure. The pressure is just the force per unit area on the walls of the container. And as you've learned in the previous section, P, the pressure, is equal to the force F divided by the cross-sectional area A. Recalling the impulse momentum change theorem, we can find the force from the change in momentum. So remember that the change in momentum, which is called the impulse, is equal to the force times the change in time. If we divide both sides by delta t, we end up with the force is equal to delta p over delta t. This is actually how Newton wrote the impulse momentum theorem, which it wasn't called then, but actually this is how he wrote his second law, that the sum of the forces is equal to dp dt. So we'll begin our derivation by finding delta P, and then we'll find delta T for a single molecule which collides with one of the very massive walls of its perfectly rigid container. So that's our goal right now, is to find F by finding first delta P and then delta T. The momentum change during a single collision of a molecule with a wall of the container is just the momentum change perpendicular to the wall. Notice here that the Y components are going to end up being parallel to the wall, and they are not going to be part of the momentum. What is going to be part of the momentum, though, is your initial x velocity and your final x velocity, because they actually are the pieces that actually collide perpendicular with the wall. Since the ideal gas model, all the collisions are elastic, so that means that delta Px is going to be equal to Px, which would be mVx, minus P naught x, which is going to be mV naught x, and that's going to end up giving us Px minus negative Px, because it's a perfectly elastic collision. There is no change in velocity, or in other words, no change in kinetic energy. That means that delta Px is going to be equal to 2 times Px, which is going to be 2 times mVx. These collisions occur for every time interval delta t, which is the time it takes for the molecule to travel from one side of the box here to the other side and then back again. So in other words, the molecule or the atom travels a distance of 2L, where L is the length of the box. So 2L, which is the distance traveled, is going to be equal to V sub x times delta t. If we solve for delta t, it ends up being equal to 2L, the total distance traveled, divided by the speed in the x direction of the molecule or the atom. The time between the collisions is going to be very small. Combining what we've gathered so far, remember we know that delta F sub x is equal to delta Px over delta T. Delta Px is going to be equal to 2Px, which is equal to 2mV sub x. And we know that delta T is going to be equal to 2L over V sub x. If we substitute in the 2mV sub x for delta Px, and the 2L over Vx for delta T, we end up with mV sub x squared divided by L. To calculate the force due to all of the molecules in the box, we would have to add the forces contributed from each molecule. So if we factor out the m and the L, because the length of the box doesn't change, and the mass of the molecule or the atoms do not change if it's the same atom or molecule throughout the gas, then we end up with the summation of the Vx squareds for each particle, all the way to n number of particles. Dividing the average value of the square of the x component of the velocity, as the average value is this summation divided by n, where n is the total number of particles, we then get an average value for Vx squared. We find that the force on the wall due to all the molecules is then going to be m over L times capital N times Vx squared. Now you may be thinking, well, wait a minute, where did the n come from? Well, the n comes from right here. We're taking this whole term, which is here. But what does that equal to? Well, we would have to multiply n by both sides. So basically, we're going to take n and n. And then we're going to replace this piece right here, which is also this piece right here, with the n v sub x squared. So here we go. So our force in the x direction is equal to the mass of the particle divided by L times the number of particles times the speed of the particle in the x direction squared, and that's the average speed. The velocity in one direction can be related to the speed using the Pythagorean theorem. So the average v squared is equal to vx squared plus vy squared plus vz squared. Since all molecules move in random directions and there's no preference between x, y, and z, we can say that it's going to be the same amount of speed, or the magnitude's going to be the same for the average Vx squared, which will be equal to the average Vy squared, which will be equal to the average of Vz squared. Okay, because there's all random directions, we can say that it's going to be 1/3 of the total speed squared is going to be each piece. It'll travel 1/3 in the x, 1/3 in the y, 1/3 in the z. So if we replace this Vx squared, we can replace it with 1/3 V squared, where V is the speed, average speed, sorry, V squared is the average speed squared of all of the molecules that collide with the wall. So we end up with the mass of the particle divided by 3L, where L is the length of the box, times N, which is the number of particles we have in the gas, times the average speed of them squared. Recalling that the pressure is equal to the force per unit area, and that volume is equal to the length times the cross-sectional area, we can replace the L with the V, and we can multiply that by A. So here we have force divided by area. So if you take this force, divide it by area, area times the length right here gives you the volume, which you have right here. Okay. The pressure in an ideal gas is directly proportional then to the average speed squared of the molecules. Since the kinetic energy is equal to 1/2 mv squared, and this would be the average kinetic energy, which means we would take the average speed squared, we can rewrite our expression for the pressure of the gas. It would then be equal to, and we're going to multiply both sides by V. Okay, so if you look at the previous equation here, what we're going to do is we're going to multiply both sides by V, and now we have 1/3 mn average V squared. Okay, and we know that the kinetic energy is equal to 1/2 mv squared. So basically we're taking this here and we're manipulating it to solve for m, and then we're substituting that in for the m here. And so we end up with PV equals 2/3 n times the average kinetic energy. Comparing this to the ideal gas law that emerged from experiments, we know that PV equals nRT, or PV equals capital N KT, where K is the Boltzmann constant, and N is the number of moles, and R is your gas constant. Okay, once you substitute that in, or this in, we have this is equal to the 2/3 N average kinetic energy, right? That means that the average kinetic energy of the molecule or the atom is going to be equal to 3/2 kT. So the average kinetic energy of the molecule in a gas is directly proportional to its absolute temperature. This is the most important result that comes out of the kinetic theory of gases. The higher the temperature, the faster the molecules are going to move on average. Now, comparing the 1/2 mv squared and 3/2 kT, we can then solve for the square root of V, or the average of V squared. We call that the RMS velocity, or the RMS speed, which means root mean square. It means you're taking the square root of the average of V squared. And if we take the square root of both sides, we end up with the square root of 3 kT over m. The higher the temperature, the faster the molecules move on average. So let's summarize our equations. We have pressure is equal to 1/3 times the mass times the number of particles times the average speed squared divided by the volume. The pressure in the ideal gas is directly proportional to the average square of the velocity of the molecules. We also have that the kinetic energy, or average kinetic energy, is equal to 3/2 kT. Temperature was explained on the microscopic level. The average kinetic energy of the molecules in a gas is directly proportional to the absolute temperature. The temperature cannot be negative and can only reach absolute value when the average kinetic energy of those molecules is 0. The root mean square velocity is equal to the square root of 3 kT over m. The average velocity of the molecules depends on the absolute temperature and the molecular mass. Increasing temperature causes the molecules to move faster. The lighter the molecule, the faster it moves. If the average kinetic energy of molecules is increased while the number of molecules and the container volume are kept constant, what happens to the pressure of an ideal gas? Does it A, increase, B, decrease, C, remain constant, D, decrease and then increase, E, none of the above? Okay, so let's take a look at your answer and see if it matches the one given. The correct answer is A. PV is equal to 2/3 N times the average kinetic energy. If N over V is kept constant, but KE increases, then P must also increase. The average kinetic energy of molecules can be increased by increasing which of the following? A, pressure, B, volume, C, temperature, D, number of molecules, E, none of the above. Okay, so let's see if your answer matches. The correct answer is C, the temperature. The average kinetic energy is equal to 3/2 kT. If T is raised, the kinetic energy must also increase. If the temperature of an ideal gas is increased from 300 Kelvin to 600 Kelvin, what happens to the average kinetic energy of the molecules? A, it doubles. B, it quadruples. C, it reduces by 1/2. D, it reduces by 1/4. So let's take a look and see if you have the right answer. Again, pause the video if you need to. The correct answer is A. Remember that the average kinetic energy is proportional to the temperature. So if the temperature is doubled, the average kinetic energy also doubles. If the temperature of an ideal gas is increased from 25 Celsius to 50 Celsius, what happens to the average kinetic energy of the molecules? A, it doubles. B, it quadruples. C, it is cut to 1/2. D, it is cut to 1/4. E, it slightly increases. Pause the video if you need to. Let's check and see if you have the right answer. The correct answer is E in this case. You may have thought, well, wait a minute, it's doubled, so therefore it should be A. But you have to remember that you have to use absolute temperature in the formula. So when we're looking at the average kinetic energy, it's proportional to the absolute temperature. So T actually only increases from 298 to 323 when you convert it to Kelvin. So the kinetic energy is raised slightly. If the absolute temperature of an ideal gas is doubled, what happens to the average speed of the molecules? A, it doubles. B, it quadruples. C, it increases by the square root of 2. D, it decreases by the square root of 2. E, it remains unchanged. So let's take a look at the correct answers. The correct answer for this problem is C. The root mean square speed is going to be equal to the square root of 3 kT over m. If the temperature is doubled, then the root mean square velocity is going to increase by the square root of 2. In the next video, we'll talk about internal energy.